In the last lecture, we stopped in this slide, right? So we'll start from there now. So this is another problem solving that we'd like to do using the lime soda softening process. So these are very intuitive type of problem. So first thing is determine the lime soda as dose in milligram per liter as calcium carbonate to soften the following water to a final hardness of 78.0 milligram per liter as calcium carbonate. The ion concentration reported below are all in milligram per liter as calcium carbonate. Means we don't need to do the conversion. Everything is given here as calcium carbonate. That means their units are the same. Okay, their units are the same. So what I did here, I just did this one. I plotted this. So this is 0. Left side would be the carbon dioxide is 10 milligram per liter. Carbonate is calcium is 120 and magnesium is 30, means from here to here. So total would be 0, 120, 150 milligram per liter as calcium carbonate. So everything is milligram per liter as calcium carbonate, and bicarbonate was 70, right? Bicarbonate was 70. I put it in there. So I didn't do anything here. This would be my non-carbonate hardness, right? This would be my non-carbonate hardness. I didn't need to show you there. So carbon dioxide does not contribute to the hardness. That means total hardness is ultimately, you can say this one, total hardness, and the carbonate hardness is 70. This one, right? Color, you remember the color here, and this would be calcium oxide. Then non-carbonate hardness initial would be this much, right? This we can calculate from 150 minus 70 is 80. This is olive color. This is a kind of, like, say, what color is that? Kind of greenish, right? Light green or so. Then we'll calculate the lime in there. So calculate the lime, basically carbon dioxide amount is the 10. Then the lime amount is what is called, the lime is bicarbonate amount is 70. Then magnesium minus 40 in this case, since my magnesium is 30 only, so magnesium minus 40 will give me only what, negative 10 means 0. I don't need to add anything. Then I have to go to the flow chart. You remember the flow chart? So flow chart was like, say, then go to the second step saying that, okay, is it greater than 40? Then in this case, since it is 0, no. Then if you go to the left side, then it will tell you just 20. Okay, so this part comes from basically from the flowchart that I showed you before. Okay, the excess lime is 20. That means this 20 is coming over here. So that means 100. Total is 100. The amount of lime soda, the lime to add is 100 milligram per liter as calcium carbonate. Now we have to go back and convert into as calcium oxide. That means in this case, the equation that we used to convert as calcium carbonate, the equivalent weight of calcium carbonate was at the top, right? Now here will be the equivalent weight of this is calcium oxide, and this is equivalent weight of calcium carbonate. So that's why we are converting from as calcium carbonate to as calcium. Okay, that means I got 56 as calcium oxide. Then if I say I have a 5% impurities, then I have to multiply with 1.05, that I get 58.8 milligram per liter as calcium oxide. That means I need 58.8 milligram per liter of water to treat. So that's what the meaning of this. Okay, so then here is the equivalent weight of calcium oxide that I calculated here. Okay, now next step is the amount of non-carbonate hardness that we have to remove. So the amount of NCH that can be left into the system, that means the final, is 78. You remember the 78 was the final hardness that we bring it down. Minus 40. This 40 is, I think I circled this one before. That is says the minimum that we can achieve for the calcium hardness is 30, and the minimum that you can achieve is the magnesium hardness is 10. Total 30 plus 10 is 40, right? So that's 40 is here. Then equal to 38 is a green color, sorry, a blue color, right? This is a blue color. So we remember that part. So NCH must be removed. So if I have initial I had 80 in the other page. You remember that olive color, right? So think this one. This is the one here. So then we know 80, and that means must be removed. How much we have to remove? That means we have to remove, this is, we can be left into the system, right? So this one can be left into the system. So we have total is whatever we have to remove is 80 minus 38. 80 came from what about the over there total hardness? This is hardness we can left into the system. So removable amount is 42. So the amount of soda that we have to use, if you go back to the flowchart, is the similar amount as like say non-carbon hardness that we have to remove. So that means it's 42 milligram per liter as calcium carbonate. Now we have to convert this one as sodium carbonate. So 42 times, this is the equivalent weight of sodium carbonate. This is equivalent weight of calcium carbonate. I get 44.5 milligram per liter as as sodium carbonate. Then if we have a 3% impurities, then I multiplied with 1.03, then I get 45.8. That means I need 45.8 milligram per liter uh, milligram of sodium carbonate to treat 1 liter of the water. Here is the equivalent weight of sodium carbonate. Okay, so now here is another problem. Yeah, because the last problem, the magnesium minus 40 was kind of less than zero, right? It was not anything. So, but this one will give us better idea to go to the right side of the flowchart and use all of this. Here, the same way. This time we would like to bring it down to 70, and the calcium is 220, 75, magnesium 265 is bicarbonate, and carbon dioxide is 70. By the way, these are the parameters we can measure inside in water in the lab using the atomic absorption. We have turbidity, hardness meter in the lab. We should be able to calculate those in the lab. And using the atomic absorption spectrophotometer, we should be able to find the calcium, magnesium, and other things like that. Okay, the same way I did plot this one. Okay, 17 to 20, and this was 75 would be total 295. This is 265. This is the amount would be my non-carbonate hardness, right? So that much. So here is again, so total hardness is 295 as calcium carbonate. Carbonate hardness is 265. So the non-carbonate hardness initial would be 30. Remember the color, all of those, right? So now we'll calculate the lime for that. So lime, same as the carbon dioxide, lime same as the carbonate. Now we'll do the next step is magnesium minus 40. Is magnesium, first thing is magnesium is greater than 40, yes. Then you go ahead and do the negative, okay? So that means this step then leads to that. Add lime is equal to, in this case, 40, right? So 40 minus 35. That means in this case, lime is magnesium minus 40 equal to 35. So in this case, would be 35. So that's what it is here. So this amount came directly from here, the step. And is magnesium minus 40 is greater than 40? The magnesium minus 40 is 35. It's not greater than. That means no. Then is magnesium. Then if it is no, then go to the next diamond, right, in the flow chart. Then is magnesium minus 40 is less than 20? No. Then go to the next diamond. Then add lime. If it is no or yes, then go different way. Then if it is no, then goes to here. Add lime equal to magnesium minus 40 equal to 35. That means both are 35, but came from different steps. So total is 352 milligram per liter. So the amount of lime that we need to add is 352 milligram per liter as calcium carbonate. I'm converting again as calcium oxide would be 197. And if if I have a 4% impurities, then it is 205 milligram per liter. Okay. Now we'll go back to, we'll do the non-carbonate hardness here. You remember that this is 70 was, we'll bring it down to 17, and this is, remember, same way I explained the color, is 30. Okay, 30, that's what the amount of can be left into the system is 30. Now the essays that must be removed would be initial minus the final, right? So initial minus final. Initial was 30 and final is 30, so it's 0. That means we don't need to remove anything. That means add no soda in these cases to the treatment process. So that means in this case we don't need that. Okay, the next one is the ion exchange softening. Softening can be done through the ion exchange. Ion exchange means, like say, we have two different way, either ion exchange membrane or ion exchange resin. So both ion exchange resin or resin, they are equipped with sodium in there. So like a sodium. Okay, so now when we have this thing in there, the hard is coming as a calcium bicarbonate, and the sodium is in the resin, or what is called in the membrane. Then it gets the calcium gets attached to the membrane, or the resin, and it becomes sodium bicarbonate. So sodium bicarbonate means ultimately what is happening. In this case, calcium is removing and sticking to the surface or somewhere into the what is called the resin or the membrane. So R is the solid ion exchange material, either whatever call it, resin or membrane. Okay, here are more description. So ion exchange membrane or resin, they have some kind of life. So at some point they may not remove anything. Whatever the point they cannot remove anything is called the breakthrough uh, occurred. So they can be regenerated. That means they can there is a process you can strip out the calcium, magnesium, and put back the sodium in there. So here is the regeneration process looks like. Calcium, whatever was there, if I use the sodium chloride, then the calcium would be sticking to the chloride and sodium would go back to the what is called the resin, right? Or the materials or the ion exchange materials. So that's how we can regenerate the membrane or things like that, and calcium chloride can be discarded. The ion exchange material can either be naturally occurring clays, zeolites, synthetically made resin, and the membrane, all of those. Softening industry use a unit called grains of hardness per gallon of water. Is like 1 grain per gallon is equal to 17.1 milligram per liter. Then the reactor is basically by definition is a tank that can hold the water in there, right, for the purpose of treatment, mixing, and other things. Uh, Reactor can be classified based on their flow characteristics and their mixing conditions. Batch reactors, fill and draw type, and the flow reaction or continuous type of operation, materials flowing to, through, and out, and reactor at all times. The other one is one time because the batch reactor. You do the treatment process for 3 hours, 2 hours, then it's make it empty again, push the new batch in there. There are plug flow reactors. Plug flow reactors basically are completely mixed steering, completely steered tank reactor or completely mixed reactor. It's also a CMFR. So that means this one is if we have a reactor here and we have a water, then we mix it. So the idea is if we take a sample from here, there, concentration will be same. And plug flow is something like that. So if it is plug flow, different region has a different concentration, right? If I take a water from here, I'll get a one concentration, from here another, from here another concentration. So that's what it is. And detention time or retention time, the time that a fluid particle remains in the reactor, it is defined as V over Q, right? V is the volume in this case. So volume over Q will give you the time. This is called hydraulic retention time or detention time, HRT. So in our topic 5, we'll see different time also, cell retention time and things like that. T0 is the theoretical retention time. V is the volume in here, right? Q is the flow rate into basin. The reactor design. So mass balance equation we used to do the reactor design. For batch reactor, input equal to output equal to 0 because nothing is staying. And the equation for batch reactor is accumulation rate equal to transmission rate. So these are the one. We learned some of those in topic 1, right? Mass balance and other things. So definitely this background is helpful over here. Mixing and flocculation, as we mentioned, flocculation, coagulating and softening water are going to take place, needed coagulation process. So the chemical reaction that plays in the rapid mixing form and precipitate during coagulation, either alum or we mentioned all of those before. So these are nothing new. So right in this case, the precipitated form of this process must brought to contact. So the mixing helps us to bring them in contact. Without in contact, it's not going to happen. That's why mixing and flocculation goes hand to hand. And the particle that happens is basically the flux. The contacting process is called the flocculation. That's why coagulation is the main process, and flocculation is the one of the mechanism coming to the contact each other and combining them together make a bigger flock. It's called flocculation. So coagulation is the charge reduction. I think we said that before. Flocculation is a contact of particles. Here is the sum of the coagulation flocculation basin. looks like this has a pedal can move, and it can be mixing over there. So here is another one. This is a looks like power pedal, like a bicycle pedal here with a chain. So if we have a some kind of motor over here, then it could be automatic. So pedal mixture details with the powered one. Okay, so we are going to stop here in this case, and